Hey kids, welcome to my next lesson on electrostatics. Please solve this problem. Okay, Daisy, how do we solve that problem? Just use Fg equals G m1 m2 over r squared. That's right. Plug it into this formula. Fg, the force of gravity, equals big G m1 m2 over r squared. R is the distance between the objects, and G is 6.67 times 10 to the negative 11th power with some weird units over here. Good review for the AP test. Last week I showed you guys a very simple demo where I have two pieces of tape and I rip them both off the board and then they will tend to repel. I didn't do it very well, so you can't really tell. How can I make them attract? Well, they repel because they both leave negative glue on the board and become positive, so they're both positive. So check out this big brain move. I'll stick one piece of tape onto the other and I'll squish them really well so the glue gets stuck. So now I'll rip the top piece off. It'll leave glue behind, but it'll leave glue on the bottom piece. And then the bottom piece will have extra glue and be negative. The top piece will have glue missing and be positive. Yes, positive. And so you can see the attraction much better. Actually, this came out much better than last week. So there you guys go. So it was pretty obvious if you thought about it, and if you did the last practice problem from lesson 2. Electricity, static electricity, creates a force. There must be some formula for the electrostatic force because it can cause torque, it can make things move, it can establish equilibrium, all that. There must be some force. So let's figure it out. What factors might influence this force? If you have ideas, let me know. What factors might influence the electrostatic force? Yes, Hazel? The charge. That's right, the charge. I had to swish that tape and rub it really hard to really get a lot of glue transferred because glue doesn't hold that much charge. I had to rub it really hard to transfer a lot of charge. So one thing is the charge. Wait a second. Hazel, which charge? The charge on the top piece of tape or the charge on the bottom piece of tape? Both, Mr. Lamb. Yeah, great job, of course. Both pieces of tape have a separate charge, so you need both to be charged. Q1 and Q2. That's good. But you could also figure this out because there needs to be two charges. Remember that similar charges repel, opposite charges attract. So you need to know both charges in order to find the answer. And we'll come back to that later. That's good. What else did you guys notice? What do I have to do with the tape to make them attract? Yes, Sage? Put them real close together. That's right. They have to be really, really close together. Super close. So another factor, just like gravity, really similar, the distance between the objects. And that r, the distance between them, is squared. Right? Right. This one, why is it squared? Well, Daisy, I told you guys when we did gravity, so I don't think you really need to hear it again. Oh, what's that? Oh, yeah, you at home really want to hear it? Okay, fine, I'll tell you again one more time really fast. If I have a mass, it's sending out gravity waves in all directions. The amount of gravity waves in a certain area is based on the surface area of a sphere of radius r. The surface area of a sphere of radius r is 4 pi r squared. So you divide the total number of gravity waves by 4 pi r squared. The 4 pi doesn't really matter, but the r squared is very important. Are gravity waves real? Don't ask me. Ask Mr. Alani. I'm not going to deal with that. The same is true for charge, except instead of gravity waves, we have something special called electric fields, which we'll talk about next lesson too. And the electric field is shot out in all directions, and it's also spread out over the same surface area. 4 pi r squared. If you guys take AP Physics C next year, this will be really cool. This will be really helpful. But until then, all we care about is the r squared. It's spread over distance r squared because it's the surface area of a big sphere where all the electric field flows through. And another side note, another name for electric field flowing through an area is called electric flux. So the flux, it starts out in a small sphere of a small surface area, and then the electric field spreads out into a bigger sphere, bigger sphere, bigger sphere. Not that you need to know it, but the electric field strength, and thus the electric force, is based on r squared, or 1 over r squared. Because that's the surface area of the sphere. Okay. That's great. We have a great formula for Fe. Any issues with it? Do you guys see an issue with this formula? Oh, what's that? Oh. Hazel heard one. What is it, Hazel? The units don't work. That's right. We need units of newtons. It's a force. Well, we got coulombs, meters. No good. Those not newtons. So we'll introduce a constant k, and constant starts with k, so we'll use letter k. K, it must be in newtons to give us newtons at the end, meters squared to cancel with r squared, per coulomb squared to cancel these two charges. And what is it? Scientists have determined it's almost a very nice number, but it's not. 8.99 times 10 to the 9th. If you want to round, if you're only dealing with approximations, if you're in a rush, 9 times 10 to the 9th. Newton meter squared per coulomb squared. So 2 great equations for 2 great forces. We're doing great so far. Something's really strange. G is so small and K is so big. But in real life, when I rub this balloon on my head or whatever, Fe is so weak and gravity is so small. Does this make sense? Let's do a practice problem. Very simple numbers. A 1 coulomb, 1 kilogram object is 1 meter from a 1 coulomb, 1 kilogram object. Find Fe and find Fg. Let's say they're both positive. Find the force of repulsion due to their electric charge, and find the force of attraction due to gravity. And then tell me, does that make sense? Do these forces make sense? Do these numbers make sense? Well, the calculation came up pretty nice. K times 1 over 1 times 1. Electric force will be exactly this. 8.99 times 10 to the 9th newtons. Fg will be G times 1 kilogram times 1 kilogram divided by 1 meter divided by 1 meter. 6.67 times 10 to the negative 11th newtons. So yeah, this is what I was saying. Electric force is so large, gravitational force is so small, but in real life, we always see the opposite. Gravity is really, really strong and pulls us straight to the ground. But if you have to like take the balloon and rub your hair super hard in order to attract like a little tiny leaf or something off the ground. Electric force is so weak. How can that be? What's that? Because charge is so small and mass is so large. Yeah. Remember I said a coulomb is a massive, massive amount of charge? A lightning bolt is only 10 or 15 coulombs, which is a huge amount of charge. When we use m's in this equation, we usually don't use 1 kilogram, 1 kilogram. We usually use the mass of the Earth, or the mass of the moon, or the mass of the sun. So the m's are always really, really big, and the q's are always really, really small. If you guys ever like go on the playground and slide down the plastic slide and then shock your friends? You don't have a charge of like 1 coulomb, you have a charge of like 1 nanocoulomb or picocoulomb, much, much less charge. So because the q's are small and the m's are large, g is small and k is large. And it still works out. It still works great. Physics is just the best subject. Okay. Good job by us. What else are we going to talk about? Let's talk about one last fascinating idea after one small interesting idea. For this formula Fg, the answer is always positive because masses are always positive, and r is squared and g is positive. So Fg is always positive. This can have a sign. Fe can be positive or negative. What does the sign of Fe mean? Don't overthink it. Just what does it mean? Well, if both q's are positive, Fe is positive. If both q's are negative, Fe is also positive. The only time Fe is negative is if one's positive, one's negative. So it's kind of a shortcut. You pretty much already know it, but if you didn't know, you can look at the sign. If Fe is positive, the objects repel. If Fe is negative, that means that two charges are opposite, so they'll attract each other. Okay, now time for one last fascinating thing. I'm going to say, what if Q were 0? What if 1Q was like, I don't know, 50 millicoulombs, and Q2 is 0? Would Fe be 0? It seems so, but let's check. I'm going to ground my feather duster by cleaning off my camera. Okay, great. Now it's grounded, it's neutral. Charge is 0. Then I'm going to rub what little hair I have and get a small charge on the balloon. Okay, so according to the formula, the balloon has a charge, the feather duster does not. There should be no force between them. But there's a very, very small attractive force. You can see the little feather bristles wiggling a little bit. So there is some force, very weak, as we established, but not 0. Let's figure out why. Here we have a nice diagram. Here's my balloon. The whole thing's negative. And let's draw like one single feather filament. Okay, there we go. I didn't draw any signs of the feather filament. Does that mean there's no protons and no electrons? Of course not, Mr. Lamb. It has both, just an equal amount. Wow, thanks, Daisy. Great job. So it has equal number of pluses and minuses. Plus, minus, plus, minus, plus, minus. Overall, this feather, filament, fiber, whatever, is neutral. What happens when the balloon is brought very close? What will the protons do? What will the electrons do? Tell me right now. When the balloon is close to the neutral filament, the filament is not attracted or repelled because it's neutral. But inside the filament, let me draw it bigger. Inside the filament, there's protons and electrons, not drawn to scale. The protons won't move. If you said the protons move, it's okay. You'll get it next time. I believe in you. But the electrons will move. Feather is not a great conductor, but nothing in life is a perfect insulator, so the electrons will move a tiny bit. The protons are still spread out, but the electrons all move far away from the balloon. Look at this piece of feather. Overall, it's neutral, but it has two sides. Let's call it left side, right side. What can we say about the force on the left side and the force on the right side? Of course, you can say the left side is attracted, the right side's repelled. But will the forces be the same? Will they cancel perfectly? Will the attraction from the left side and the repulsion on the right side be the same amount of force? They won't be the same. K is the same. It's a constant. Q1 is the balloon. That's the same balloon. Q2, it's actually the same. If the left side loses 3 electrons and the right side gains 3 electrons, the positive charge on the left side will equal the negative charge on the right side because charge is conserved. So it's not K, Q1, or Q2 that's different. The top's all constant. R is the difference. The left side of the feather fiber is closer to the balloon. The right side is farther. So the attraction is stronger than the repulsion. Even though this little piece of whatever is neutral overall, it's attracted more than it's repelled. So a neutral object actually can attract a charged object, negative or positive. If this were positive, the electrons would just be on the other side. This is called polarization. To be specific, I would say it's an induced polarization. The negative balloon caused the hair or feather to be polarized. Polarized means there's two poles. A positive side pole and a negative pole, negative side. It's polarized. So that's how a neutral object can be attracted a little bit to a negative or positive object. It still fits this formula, but you gotta break it into two parts. One for the left side and one for the right side. So it's a lot more math. But you can do it because you're super smart. I believe in you. I think we did a great job with this lesson. So I think I'll just talk to you guys in class and we'll do the practice problems. See you then.